Well, although SPH has been around a long time, the thing that really impresses me is the quality of the work that you people are doing. It really is amazingly better than what we did when we started. What we do when we started, we were looking at astrophysics problems, but we were unable to use more than about 100 particles because the computers couldn't handle it. And therefore we were limited in what we could do. And gradually the number of particles increased, and as time went on we learned how to do everything a bit better, just like you people here are thinking about how to make things run faster or how to accommodate physical ideas better. And I thought at the time when we were started doing this, and it wasn't 77, when we started doing it, I thought we can do anything. We can mimic the heart, we can have a look at collisions with buildings, which I might say I was in a German city called Bonn, and on September the 11th, and I was giving a talk, and it was an SPE calculation of an object hitting a tower, which in this case I mimicked as the Tower of Pisa in Italy, and I had an object hitting the tower, and the tower collapsed. And when we came out, what I noticed was that everybody was around the TV. And of course they were looking at the two towers being hit by aircraft in the United States. And I thought, what a coincidence that I talked about calculating this. And it was something which you guys don't do, because we were looking at stress in materials, which was appropriate for the collision with a tower. And then I got involved with engineering, but I'm not going to talk about most of that today. I'm actually going to talk about things which partly astrophysical and partly engineering or geological, and I'm really doing it to entertain you rather than just tell you how to handle the dynamics of a disk, for example. Disks seem to be very important. Okay, now this first slide, well, first of all, I like the pictures of Kandinsky which somebody had on a slide, Manuel I think, and I want to talk about astrophysical problem, which is the three-body problem. And this was published a long time ago, and then it disappeared, but people have become interested in three-body problems, so we're having a conference in Jerusalem, provided they're not killing each other, later in the year. And the three-body problem is interesting because at that time people were doing many calculations, taking three bodies, putting them close, letting them interact, and almost invariably one of the bodies would escape, leaving a binary. So the question was, what are the properties of this binary? Well, if you do 1,000 calculations of three bodies or so, what you find out are the statistical properties of the binaries that are produced. And I thought there had to be a simpler way of doing this rather than doing all these calculations. By and large, it's a good policy to look for simplicity. So anyhow, this is the three-body problem. Astrophysically, the simplest thing is to take point particles, and when they interact, they end up with producing a single particle escaping almost invariably, not always. And that was me showing something on a board in 1985. And the integrations were done by Standish, Valtonen, Sasler and others in 1970 to 75. And I thought it should be possible to make a statistical theory because the motion is very complicated. And those of you who've done some statistical mechanics will know that very complicated problems can often be discussed in terms of phase space. So I thought I could work out this. Enrico Fermi in 1950 proposed a calculation which was statistical to understand the production of particles. And you notice 76 here, 2019 there. There's a big gap. And I was doing some work at the Department of Applied Mathematics and Theoretical Physics in Cambridge. And here is the three-body system. It's got two masses which are bound. They're separated by a distance r. These m's are the masses. The center of mass of the entire system is here, but the center of mass of the binary is there. And this distance rs goes to the escaper. And you can make many approximations, one of which was that the escaper was going so fast you could just treat it as going freely away. And the phase space is an integral over the momentum of the escaper, the position of the escaper, and then properties of the binary like r and p, which is p is the momentum of the various particles, and the basic energy, if you scale things, is a half. This is a kinetic energy term of the escaper, and this is the kinetic energy term of the binary, scaled in various ways, and this is the potential energy. So you can ask yourself, can I do this integral and find out the probability of certain things? Well, one of the you usually have to assume something, so we assumed that everything happens within a distance r, which was scaling things, and now you see the integral for the escaper is pi r squared. The integration over its momentum is 2 pi m, which is the mass of the escaper, and the plane polar coordinates for the remaining integration is just dr, dpr, d theta, dp theta. This talk is somewhat different to the usual talk because usually this week we see a binary and producing a disk. Anyhow, you make a change of variable, and this is the energy of the binary, this is the momentum p theta of the binary, and x is equal to r, and the phase space turns into this big integral, and it's a threefold integral. It depends upon the momentum and x coordinate EB, and you can integrate this exactly, and you get this final result. Now there are two integrals here. One is over the energy of the binary, which is proportional to the inverse of the semi-major axis, and here's the eccentricity, and there are a few other parameters out the front here, including this r squared. And we won't worry about that again. And here is the result. These are low angular momentum results from Bill Saslow and others. And that's a frequency, and that's E squared. And the histograms are the result of 1,000 or so numerical integrations of 3 bodies. And the full line is the statistical result. So actually the full line fits it very well. And recently, Stone and others in Jerusalem have been integrating this more exactly than I did for the complete set. And you get the results are even better. Now, Standish, for the numerical simulations, these things turn out to be more complicated than you might imagine. What he did was select 3 masses in 0 to 1, scaled. No, they were scaled in terms of some units, 0 to 1, and then he would scale them so that the total mass was 1. And you have to think about the frequency distribution after you've scaled it. Initially it's simple. It's in a cube and it's just random within a cube, but once you start scaling things, you start changing the probability distribution. And It turns out that in 2 dimensions it's pretty easy to do. Here's 2 dimensions, here's the Jacobian, here's the new variables u and v, here's u scaled, here's v scaled. That's supposed to be a comma there. This is the Jacobian, but it's infinite. Why is it infinite? Because u plus v is equal to 1, so they're not independent. So you have to do it another way, and the way is called geometric probability. And I won't go into that, but that's the way you have to do it if you choose, as Standish did, to scale things. You can also have a distribution which depends upon a delta function, which requires x1 plus x2 equal to 1. Here's an integration of some function of x1 and x2. But that would be equivalent to taking one and saying the other one is not random in the same way. It's one minus the other one in order for the mass to be the same. In 3 dimensions, the masses are scaled. The probability distribution is much more complicated. Anyhow, the results fit the numerical calculations extremely well. And if I'd wanted to, I could have done a relativistic 3-body problem and worked out the properties of it, because all I was looking for was the phase space. So that's all I wanted to tell you about the 3-body problem. If you want to know more, you need to go to Jerusalem later in the year. So now I want to talk about velocity fields. How do you start a calculation? You specify the positions of the particles, you specify their masses, and then you look for then you have to specify the velocity field. And the question is, what sort of velocity field should you specify? The usual thing is to take not entirely, a spherical cloud, a spherical gas cloud, and give it some angular momentum and evolve it. However, Chris Hunter in 1970 showed that the rotation angle in a paper which had the title "The Rotation and Angular Momentum of Galaxies" showed that almost invariably what happens if you put in angular momentum and vorticity is you don't get a disk at all initially. For a long time you get something else, a bar. And the reason for that is the vorticity. And it turns out, I mean, if you have an isothermal cloud, the vorticity is conserved. If you have a gas which is you're treating as just proportional, pressure proportional to a function of the density, the vorticity is conserved. So you have something else conserved apart from energy and angular momentum. So I did some calculations of this, but the important thing is what Chris Hunter got was ellipsoids with vorticity and angular momentum, which are spherical, perhaps starting elliptical, evolve under gravity to highly asymmetrical shapes. And what I did was to consider a velocity field which is linear in the coordinates. These A's are constants. These big A's are constants here. You have an ellipsoid with semi-major axis A1, A2 and A3. And for most of the calculations I did, I chose A1 to be square root 2, which is about 1.4, A2 to be 1, and A3 to be approximately 0.7. Now what that means is that you're starting with an ellipsoid. You're not starting with a sphere. You could take an ellipsoid and put turbulence into it, but depending upon these parameters, it has angular momentum. So what can happen is that if it's got viscosity as well, the shear which is in this will disappear, but the angular momentum will be conserved. So eventually, it's going to be a disk. spinning with the angular momentum you got. But it may take a long time for it to get to that. So zeta is the vorticity, and the vorticity depends upon these constants, and you get various other things. You can figure out what A12 is. Little f here determines the ratio of vorticity to angular momentum. If you make it large, the angular momentum gets larger. The vorticity gets larger. So here's an example of what you get. This is that ellipsoid with the parameters I spoke about. This is the angular momentum about the 3-axis. I've got vorticity also about the 3-axis. And it turns into a bar. And if it's rotating, if the rotation is rigid, it turns into a bar and material is collecting on that bar. And here's the case with f is equal to 1.5. So this is the vorticity is larger, and it turns into a bar which then breaks up into fragments. Now, if when I was doing this I had better computers, I would have run this for longer, and I would have seen this stretching out. Notice that that's a very thin filament which is stretching out. It's actually got the angular momentum which is specified within the velocity field, but it has shear as well. And if you run your calculation long enough, this will all come together and spin. But by then it will have formed fragments. Now I didn't explore the fragments, but it's possible that if you have a velocity field which is different from the standard ones, that you'll form planetesimals early on. You don't have to wait till it forms a disk to form planetesimals. They may form earlier on. So the moral of the story is what you want to do is think about the initial velocity field. And these calculations also, the initial cloud. It wasn't spherical, it was an ellipsoid. So you have to ask yourself, should I have an ellipsoid? Should it have a velocity field which contains some of these things? The answer is yes, because the world is complicated. And these things, out there in the world you have different things. That's two parts. I'm already going a bit fast, but I'm going to make some remarks about time stepping. That's Santa Barbara, where I was thinking about remarks on time stepping. First of all, time steps. You have many time steps. These are some of them: pressure, viscosity, drag, and thermal conductivity. And the coefficients depend upon the algorithm you're using, but they tell you what dt is. And k in the drag, if it's due to particles, is 1 on the grain size squared. And what we know is that if you have small dust particles, the time step is very short. And therefore the calculations take a long time unless you do something. So over the last decade or so, perhaps longer, people have been exploring ways of dealing with dust, even dust which is very tiny. And the first thing I think I did was to try and find a way which would be very fast of dealing with the dust part, but it wasn't very accurate. It was really what would be called a splitting method, but it was only accurate to have ordered delta t. And that's not accurate enough, really. What you want is something which is accurate to delta t squared. And you don't want to have to use this short time step. Now, the only way I knew of dealing with this was to use, I thought I'd show you this. I was interested in pyroclastic flows, still am actually, and This is a pyroclastic flow which has come down to the ocean from the island of Montserrat. And what you notice about that is there's dust. That's in the pyroclastic flow. What you don't notice is the temperature is about 600 to 800 degrees. You see it hitting the water. 600 to 800 degrees hitting the water produces steam. So in your calculation, you have to have steam production. So water vapor gets into the air. And it's possible for the pyroclastic flow to travel out across the water. And we did a few things on pyroclastic flows, but not this particular one. So people working in geophysics, they also are interested in dust. And just like dust in geophysics, there are many different sizes. And you have to say to yourself, how am I going to handle this in my code? Can I do it correctly? And the answer to all those things, well, you can do it. Now, I've just put these equations down here for dust and liquid. And I wrote these out when I was dealing with geophysical problems, or engineering problems which involve liquid, but it's the same thing. Some pressure, some density. This is density scaled using these parameters: volume fraction, velocity of the dust, and velocity of the liquid. And then if you convert that into SPH, oh, here's a typical drag coefficient for the geophysical problem. You notice that there are various things: the viscosity of the fluid, the volume fraction, some function of the velocity difference between the dust and the fluid. And this is the grain size squared, and this is theta L to 1.65. What I discovered was that engineers who deal with dust, and all kind of chemical engineers who deal with dust, they don't always have a formula. I mean, they don't derive it analytically. But what they can figure out is that certain things should come into it, like the volume fraction of the dust. So what they do is run experiments down some kind of tunnel. They run these experiments and they figure out what coefficient, what power fits it best. Now, of course, in some respects, this is not really satisfactory. Why? Because you don't know what will happen if you change the tunnel where you're running this from square cross-section to circular cross-section. Or if it has a bend in it, where you still get the same coefficient. And you look at their formulae, and what you notice is, not this one, but quite often they have something like 1.7325. And once you see all those decimal places, you know that they've got it from one particular set of experiments, and it's not going to apply to anything else, really, or something like that. Anyhow, that's a typical drag coefficient that these people use. Now, this, well, you will have seen this. This is the SPH acceleration equation. The pressure terms for the fluid, dust, fluid interaction. B is a fluid, J tags a dust particle. VJA is VJ minus VA, RJA is RJ minus RA, and KAJ just refers to the drag coefficient, which depends upon quantities involving fluid A and dust J. And then for the problems that I'm interested in, where you have walls, like that pyroclastic flow, you treat the boundary of the ground and the cliffs as walls. That comes in here, but we're not going to discuss that today. And it's got gravity. And you could write this as D column vector V is some F which is this kind of term, and this term, and then a matrix A times V, and that's this term here, which determines the interaction between dust and gas, or dust and liquid. And in the case of the pyroclastic flow, you have gas, dust, and steam and water. Now, I wanted to tell you about time stepping. There are two parts of this time stepping. First of all, you step half delta t, that is to the midpoint of the step, and this makes use of pressure and viscous terms. And then you do a second one which involves the drag term, which is this one here. This one has come from the pressure and density. And then you have a final one which involves integrating r, rho and theta a further half delta t. Now this comes about because, first of all, you just use the pressure and viscosity and gravity. You solve for V star, then use this velocity to do the drag. And in the drag, rho, P, rho, theta and R can be taken as constant because they're midpoint values. The matrix A, which we saw before, is really a lot of 2 by 2 matrices. So you take pairs. So here's an example. Now, those of you who are nearly asleep, this will help you. This is a dV dt is A1 plus A2 times V. You can write the integration as this exponential operator acting on V initially. That's t, and this is t plus delta t. You can approximate it by a product. And what this product means is, this is the differential equation, here it is here. Then, when you've integrated it, you've got new V's, and then you use this, which is a differential equation, to take it to the final stage. So there are 2 lots of delta t integrations, and the unfortunate thing about it is only first order accurate. But you want it second order accurate, at least. So second order accurate means you have to integrate over A1, the differential equation, then the differential equation with A2, then do A2 again, another integration with another delta t, and then you do A1 again. So you do it in reverse order, and then it's second order accurate. It's kind of interesting, and it's very easy, at least with a serial computer, to write a code to do this. But I have to tell you, I couldn't think of a good way of doing it with a parallel computer. And I'm not sure. By the way, Steve, is the sound coming through? Good. So I wasn't sure how to do it for that, but I was able to do it for other cases. So for example, if you have a fluid particle and a dust particle, this S involves the drag, W is a kernel, and it turns out that if you subtract these, you get an equation for VA minus VG, and R bar just means the midpoint R, so you don't have to worry about that again. That's a constant as far as this is concerned. And you can integrate this, subtract the 2 of them, and then integrate to get VAJ dot RAJ. And so you subtract it, you dot it with this R bar AJ, and you can integrate it. So you get VA1 is equal to all this stuff, an exponential in there, and you get a similar equation for the dust velocity. Now this is kind of nice because you can integrate all these. Now K may be complicated, so if it is very complicated, you can't do the integration, but even if it's quadratic in the velocity, you can do it. Now here is some particles which have 250 microns in radius. And that's quite a big radius, and here it's settling down in a tank and gradually goes down to the base under gravity. This one is 25 microns, and in the time that this is run, it doesn't sediment. Now I want to show you, this is a similarity solution by Herbert Hubbard for, this is equivalent to lava. The ratio of the viscous time step, the ratio of the two of them is 6.3. That is, the viscous time step should be 6.3 times smaller. And it is 6.3 times smaller, but if you had an explicit calculation, you wouldn't be able to integrate it. Anyhow, the SVH calculation is this full line, and the similarity solution is the dotted line, which disappears into this. So X knows is how far this is along, and T is the time. Now this is one for Hawai Basalt, and the viscosity is 300,000 times the viscosity of water, and you can do the integrations easily enough. The time step is actually the time step for the Courant time step. You don't have to worry about the viscous time step. You're taking care of that because you're integrating exactly. And this fits in the Herbert Hubbard kind of way of doing it. Now I'm going to stop there. I've still got about 10 minutes, I think. 5? So the problems which remain in this is how to do this time stepping for a parallel code, because it turns out that it's not trivial to do that. But if you can figure out how to do it, you'll be able to run a dust calculation very efficiently, and that's something which I will leave you to do. I couldn't think of how to do it a year ago, and I'm sure somebody here will think of a way of doing it. So that's the take-home message for that. So I'm going to stop there, and thank you for listening to me.
Just, this is coming from my completely ignorance about pyroclastic material and simulations doing simulate them. But when the lava hits the water and you have like this huge steam generation.
Yes.
Well, it's a really violent and you could say almost instantaneous reaction, which leads me to think about Riemann discontinuities, right? Because you have a certain change in the pressure of water that you didn't account until the lava arrived there. So if that's the case, because I'm not really too knowledgeable of this, how can you solve that, or how do you solve that in those simulations? If there's in fact a discontinuity in pressure due to the water turning into vapor instantaneously.
You think that's a problem?
I don't know. That's why I'm asking.
Well, as far as water is concerned, there are no problems like that. It's actually quite easy to integrate them. And without fully answering your question, I went to a talk given here at Monash many years ago on the Minoans, and in particular what happened to the people on an island that's called Thera, or these days Santorini. And I said to the speaker, I could do this calculation with SPH. And then I thought, well, I can do this calculation, but you just have to have a pressure term for the water, and then everything just goes the way SPH goes. And we ended up actually going to Santorini and doing coring and calculating various things. So I could be just talking about wonderful archaeological problems, but I stopped doing that after a few years and went back to some engineering problems. But there's no difficulty at integrating these.
Yeah, no, that my question was not if it was hard to integrate, but if were actually a thing that you should take into consideration or not. But I think that's
Really?
I don't know.
Well, we'll talk about this later, I think.
Sure.
You have a question for Joe?
By the way, I didn't mention it when I was giving the talk. The time stepping with splitting can be used for heat conduction or heat diffusion or radiation diffusion with the proviso that I'm not sure how to handle the something in a parallel code. But you can do it, the same thing. When you're trying to solve these problems, you should approach it the way Sun Tzu, the famous Chinese general, approached war. Now, he said one of the things that you have to do is find out what are the properties of your enemy. There's a wonderful book called The Art of War, written by Sun Tzu. And it's true in this case. I mean, the enemy in your integration is really the term which forces you to use a short time step. So you concentrate on how you deal with that. In the case of radiation, you may have a short time step, and that's your enemy. And you have to find a way of defeating your enemy. There are some other wise things in the book on the art of war. He said it's a big disadvantage if you actually have to fight. You should find some other way of defeating your enemy rather than fighting. So if you're finding having a problem with a short time step, as I say, treat the term in your equation as the enemy, and you're going to defeat the enemy in the war that you're conducting.
Yeah, I had a question regarding the first part of your talk about the statistical approach of the three-body problem. You said that you were picking like the position of the particles randomly, but could you comment on how this distribution depends on the mass ratio or taking different masses? Because I think you mentioned that in the energy equation there were terms depending on different masses.
Yes.
But in your distribution, when you show the integration,
You have to, well, if you want to know the mass distribution, you have to think about how the masses are produced, how you choose them, and without going into detail, because I can't remember the details, in general, the smallest particle, by small I mean least mass particle, is the one that escapes.
yeah, this was later confirmed numerically, but that comes from your statistical approach.
Both the numerical simulations which people had done, but also from the from the statistical distribution.
I was just curious about conservation of vorticity or circulation. So do you think conservation of circulation or the initial circulation is something we should worry about in things like common envelope evolution, like stellar binary interaction?
I'm not sure. If you have, if you think about conservation of circulation, then it is exact if there's no viscosity, and if you have for example, pressure which constant temperature, and it would be exact if you have pressure a function of density. But in these calculations that I ran, I had molecular cooling, and I can't remember what else I had in there, but it wasn't conserved exactly. But things don't have to be conserved exactly in the circulation to affect the evolution of the velocity field. But the first thing I would do, I think, if I went off here, would be to make an ellipsoid to start with. I mean, that ellipsoid had axes 1, root 2, 1.4, and 0.7. So one of the axes was about half the largest, not the largest one, but half one of them. And that's enough to trigger off forming a bar or a long filament. And if you have a long material in a long filament, it's actually easier for the dust to come together in the filament because you have local gravity and the scale is smaller. And I think I think it would be reasonable to ask a student to explore the effects of some of these things.
Yes.
Not me, you.
Alright, let's join Joe again.